All right, in this video, we'll look at question 2 on the worksheet that says, let R be the unit square here in the first quadrant with side lengths of 1. And part A says, if the square has uniform density, what's the location of the center of mass? Answer this with a calculation and without a calculation. And as we saw in the one-dimensional case, with uniform density, center of mass is referred to as the centroid of the region. Okay, it's also referred to as the geometric center of the region. And so with this kind of a nice shape, well, the geometric center will be just right smack dab in the middle here, right? So without calculation, we can just see that the center of mass will be at the location 1/2, 1/2. Now, of course, to do the calculations, first note that since we're assuming uniform density, that just says the density function rho is equal to k for some constant k. And so our mass calculation would just be the double integral over our region of that constant. And notice if I just integrate a constant dA over a region, that's just going to give you k times the area of that region. And since we're integrating over a unit square, that area there is 1, so the mass here would just be k. All right, now for the two moments, we have the moment about the y-axis, that's the double integral over our region of x times our density function. So be careful there again. Remember for the y moment, right, the integrand has an x times the density. It can be a bit confusing, but remember x there is a measurement of our location to the y-axis. Okay, so that's why you see that x. Well, in any event, I'll go ahead and take the k out, and then we're just going to integrate x over that region, and so that's going to give you k over 2. Okay, now for the x moment, okay, we're going to have y times the density, and so taking the k out, we're going to integrate y over that region, so that again give you k over 2, and then so for the center of mass, the x coordinate x bar is the y moment divided by the mass, which would be k over 2 divided by k, and that's equal to 1/2, and likewise there for the y coordinate y bar. So through the calculation, we also conclude that the center of mass is just at that geometric center point of 1/2, 1/2. All right, cool. So now let's go ahead and check out part B. So now our density function rho is equal to 1 over 1 plus y. So first, a few comments about how the mass is distributed throughout the region. So if y is, say, equal to 0, okay, so we're going to be on the x-axis, our density will be as large as possible. It'll have a value there of 1. And now as we let y increase, our density is going to decrease. Okay, so we're going to be less dense towards this upper region of our upper portion of our region, and then we're going to be more dense down here towards the x-axis at the bottom. The other thing to notice is that this density function is independent of x. So if I imagine drawing two vertical strips, okay, the density will be distributed in the same way along those two vertical strips. Okay, so now let's go ahead and get into the calculations. So for the mass, we're going to integrate our density function 1 over 1 plus y over our region, and that's going to give us a logarithm, and I'm omitting a few of the details there, but it's a pretty straightforward calculation. And we get that the mass of our region is the natural log of 2. For the two moments here, well, the moment about the y-axis, that's going to be x times our density, so x over 1 plus y. And integrating that, notice I could split this up as a product of the single variable integrals, where I have just the integral of x dx from 0 to 1, and the integral of 1 over 1 plus y dy from 0 to 1. And the x integral will give us 1/2, and the y integral will give us the log 2. So altogether, you have 1/2 log 2 for the y moment. Okay, for the x moment, you have to integrate y times your density, so that'd be y over 1 plus y. And now to integrate this, you want to rewrite it as 1 minus 1 over 1 plus y. Okay, and you could rewrite that using long division, or maybe a bit more simply, you could just note that the numerator can be rewritten as 1 plus y minus 1. So in other words, add 1 and take away 1. Then splitting this into two fractions, you get 1 plus y over itself, that's 1, minus 1 over 1 plus y. Okay, so now you could split this integral up into two pieces. The integral of 1 is just the area of the square, which is 1. In the integral of 1 over 1 plus y, well, that was the same integral we had for our mass calculation, and that's log 2. So altogether, your x moment would be 1 minus log 2. Center of mass then, for the x coordinate here, x bar, we take the y moment divided by the mass. So we get 1 half log 2 divided by log 2. That comes out to be a half. For the y coordinate here, y bar, we take the x moment, divide it by the mass, so we get 1 minus log 2 divided by log 2, and this comes out to be roughly about 0.443, just using a calculator. So altogether then, we conclude here that the center mass, x bar, y bar, is located at 1 half, comma 1 minus log 2 all over log 2, which is about 1 half comma 0.443. Okay, so now last thing I want to comment on here is just in terms of our location. Well, x is 1 half, and then y is a little bit less than a half, so we're, maybe down here a little bit. Now, this makes actually a lot of sense given, as we said up above, our density is independent of x. So it makes sense that the balance point here would be, well, in terms of just the x interval itself, the midpoint of this interval from 0 to 1. Okay, now also, as we said, the density decreases as we let y increase. So we're less dense up here and more dense down here, so it makes sense that this center of mass point would be shifted down a little bit. All right, well, that's going to do it for this question. See ya in the next problem.